Okay, everyone. So in this homework, I'm going to take you through the solutions to assignment 43B, which has some really good calculations in finding absolute extrema in a couple of different settings. So the first thing is, we want to look at the question with these trigger words. Find the maximum and minimum. And that, of course, means absolute. So they're not local maxes or mins. They are absolutes. They are the biggest y's and the smallest y's. So the first thing we're going to check for is whether or not the function is continuous on a closed interval. And this function is a polynomial function, which is continuous for all reals, and in particular on that closed interval. So when the function f is continuous on a closed interval, it means that EBT applies. So the first question is, when we see we're finding an absolute max or min, we're either going to invoke EBT, the closed candidate test, or we're going to do a global argument, which we've talked about. So since this function f, again, is continuous on this closed interval, we're going to invoke the closed candidate test. And hopefully I have enough room here. That entails the first step is to take the derivative, which would be 12x squared plus 6x minus 6. Set the derivative equal to 0 because that's an important step in getting what's known as our critical points. I took out in 6, which would give me 2x squared plus x minus 1. And I'm going to reverse FOIL that, as I say. And I think I'll need the 1 here in the positive and the minus 1, because that'll give me 2x minus 1x is a positive 1x. And my critical points are 1/2 and minus 1. Just make sure that these critical points are within that closed interval, and they are. So simply put, build a table of values. The endpoint is -2, the critical point is -1, and then we got 1/2 to worry about as well as 1. So sometimes on the AP exam, you will have to do this computation. So just make sure that you're comfortable substituting these values in. 1 is pretty easy here. 7 minus 6 is 1 plus 1 is 2. If I did minus 1 pretty fast, that's going to give me -4 plus 3 plus 6 plus 1. I'm just going to sub in that minus 1 for x, and I think that looks pretty good to me there. So that's -1 plus 6 is 5 plus 1 is 6 right there. And the rest you could also do by calculator. The -2 is okay, but to be a little faster, I'm just going to use the calculator here and show you how to do this all at once. I just need to do a little split screen here so that we have enough room for everything. That makes it a little better. Okay, so go to second quit. I'm going to do it on my screen. Go to y equals. I'm going to clear this out. I'm going to put in my function. So it'd be 4x caret cubed plus 3x squared minus 6x plus 1. Second quit. And what I'm going to do this time is I'm going to do second table. And the second table feature, you may want to do maybe for a second table set. So second window is table set, and just hit independent ask. So cursor on top of ask in the independent option, it's going to prompt you for an x value. And then when I hit second table, I'm just going to put in my values, -2, -1, see if I'm right there, and 1/2 or 0.5, as well as 1. And that'll give me all my outputs. -7, 6 was correct, -0.75 or -3/4, and then 2. So this is my maximum value. It's the biggest y, and that's my minimum, the smallest y. Okay, I think that's the only one I really needed that for. I think the rest are all pretty good. All right, down here in number 2, we have to do a product rule. We're to find a max and a min. The EBT applies because the function's continuous in a closed interval. So again, not to be scattered, because you have to know what the approach is as soon as you read these trigger words. So you're to find a max or a min. You're either going to do the closed candidate test or the global argument. If you're continuous on a closed interval, we're going to do the closed candidate test. So G prime is a product rule. The first times the derivative of the second, which would be minus sign, plus the second times the derivative of the first. And that cleans up to be minus sine squared plus cosine squared x. Set it equal to 0. The only way you can handle this trig equation is when sine and cosine, as well as sine squared and cosine squared, are being added or subtracted, is to convert that in terms of tangent. So what I'll do is I'll subtract the cosine squared and divide by the negative cosine squared, and then I'll get tangent squared x equals 1. So I just want to make sure I did that okay. So I did sine times negative sine plus cosine times cosine on a product rule. That's negative sine squared plus cosine squared equals 1. And that's took over the cosine squared, made it negative. Divide by the negative cosine squared, and I'm going to get tangent squared x equals 1. So be careful though, tangent x equals plus or minus 1, because you undo the square by plus or minus the square root. Now I have to do, this is where tangent's positive 1, and that is going to be a reference angle of pi over 4. And here in these two quadrants, this is where tangent's negative. In all cases, the reference angle is pi over 4. So in the first quadrant, the answer is pi over 4. In the second quadrant, it's 3 pi over 4. In the third, it's 5 pi over 4. And in the fourth, it's 7 pi over 4. And we need this time a table of values. So it's going to be pi over, oh, sorry about that. We've got 0. We've got pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, and 2 pi. The nice part, guys, about this one is you sub in the 0 for here. The sign of 0 is 0, as well as the sine of 2 pi times the cosine of 2 pi is also 0. So that makes that pretty nice. And the next thing you're to do is to do the sine of pi over 4 times the cosine of pi over 4. In each of these cases, that's 1 over root 2 times 1 over root 2, or 1/2. The sine of 3 pi over 4 times the cosine of 3 pi over 4. Well, the sine of 3 pi over 4 is 1 over root 2, and the cosine of 3 pi over 4 is negative 1 over root 2, and these multiplied is negative 1/2. And these values are going to repeat as you do 5 pi over 4 and 7 pi over 4. You will get 1/2 and you will get negative 1/2. This is your minimum, is negative 1/2, and positive 1/2 is your maximum, the biggest y. In the next problem, we are not on a closed interval. So the closed candidate test is out, and we're going to do the global argument. So that means in both cases, I always take the derivative. In this case, that derivative would be 1 over 2 root of x minus 1. Please, in getting the critical points, you got to get a common denominator. The way you clean up a derivative is to get a common denominator or factor. So I'm going to times this by 2 root of x over 2 root of x. Not do that. Let's do 2 root of x that way. So my new numerator is 1 minus 2 root of x over 2 root of x equals 0. 1 minus 2 root of x equals 0. And I get here root of x equals 1/2, and x is 1/4. When I set the denominator equal to 0, x cannot be 0. I'm sorry, x can be 0 because here I did see that the domain is from 0 and above. So remember, to be a valid critical point, the number's got to be in the domain of the function. So this starts at 0, and my only critical point is 1/4. Again, there's no chart in this. We're doing the global argument. This closed candidate test does not apply, which means we cannot do a table of values. We got to take the derivative, do a number line test, and hope that on that number line, the derivative only changes signs once. So as a great test point, I'm going to pick 1/16 because that's smaller than 1/4. And when I sub in the 1/16, again, it's just a little tedious computation. the square root of 1/16 is 1/4 times 2 is 1/2. And 1 minus that 1/2 is a positive. And if I pick, say, 9, I'm clearly going to get a negative. Since my derivative only changes from a positive to negative, I have an absolute max at x equals 1/4. So x equals 1/4 is where the max occurs because f prime only changes signs from positive to negative at x equals 1/4. And the actual maximum value is found by subbing in the 1/4. So the square root of a quarter is a half. Come on, we just got to push through. Times this by 2/2, get a common denominator. 2/4 minus 1/4 is 1/4. So that is the actual, end result there. And just to do a few more selected problems here, is this one right here of a piecewise function. So is the function, I'm sorry, we have to find the maximum value. So does the closed candidate test apply or a global argument? So are we continuous? Well, these are both continuous functions or polynomials. When I check the endpoint at 1, 4 equals 4, so it's good to go. All right, so the first case is to take the derivative of the top piece, which is 2, and the bottom piece, which is 8x. So then I'm going to set the derivative equal to 0. So this top piece 2 never equals 0, but 8x equals 0 when x equals 0. Now the only problem is 0's not within that, guys. 0's not within that. So therefore that's not going to be a valid critical point. But this function, the derivative at 1 is a D&E because the slope from the left of 1 is 2 and the slope from the right of 1 is 8. That slope does not exist at 1, but the function is continuous at 1, which means 1 is a critical point. So what am I going to do? Just go right to when the closed candidate test applies. You just build a chart with the endpoints and the interior critical points. So your endpoints are 0 and 3, and the only interior critical point you have is 1. Put in the 0 for x, you get 2. Put in 1 for x, and I'll get 4. And put in the 3, and I'll get 36. And that is the maximum value. Again, class, the reason why 1 is a critical point is because the function's continuous there, but we have that corner point. On the graph of this at 1, you've got this line, and then you've got this parabola, which is, pretty steep through there, and the slopes just don't, they just don't become one value. So that's why 1 is a critical point there. The next one is this function down here, g. Again, do we do the closed candidate test or a global argument? We're not on a closed interval at all, so this is out. So the closed candidate test is in. So I got to do the derivative, which is a quotient rule, the bottom times the root of the top minus the top times the root of the bottom. All over the bottom squared. This cleans up to be x minus 2x times ln of x over x to the 4th. Now, what's nice about this is, again, factoring is the name of the game and cleaning up a derivative. So I know I'm going to run out of room here, right? So and there we have it. So I'm going to set the top equal to 0 and 1 minus 2 ln of x equals 0. And x equals e to the 1/2. So all I did there was subtract 1, divide by -2, and the undue ln is always base e, so x equals e to the 1/2. X cannot be equal to 0 here because 0 is not in the domain of the function. When you have an ln, In this case, x must be greater than 0. So I'm going to do a number line test on e to the 1/2, and this is g prime. Now, what's bigger than e to the 1/2 is e to the 3rd. I'm going to put that into my derivative, everyone, which is right here. So 1 minus 2 ln of e to the 3rd. This is just 3. ln of e to the 3rd is 3 times minus 2 is minus 6, which is a negative 5, over a positive is a negative. Wrong spot, though. And then if I pick e to the 1/4, that's going to be 1 minus 2 ln of e to the 1/4. Well, the ln of e to the 1/4 is 1/4 times 2 is 1/2, and 1 minus a half is a positive. So since this derivative only changes signs exactly once from positive to negative, I have an absolute max at x equals e to the 1/2. So it is absolute max at x equals e to the 1/2 because g prime only changes signs from positive to negative there. But remember, when it says find the absolute maximum, that's a y value, not an x. So what do I have to do? Well, guys, I have to sub that back in. So ln of e to the 1/2 over e to the 1/2 squared. That's 1/2. E to the 1/2 squared means power to a power. So I'm going to multiply. So it's going to be e. So my answer is 1 over 2e. This is the absolute maximum right there. And I think I'd asked to do a particle motion problem here. So I'm just, doing selected problems, so it's not too long. Here in this one, we're to find the maximum height of the object. So then if this is my height function, and I want to know when, the maximum height, that's the same thing as an absolute maximum. So again, that's the trigger word, which means closed candidate test or the global argument. I'm only on a time frame from 0 to infinity. That's not a closed interval. So therefore, it's going to be the global argument. So if this is the position of that object being tossed upward, I'm going to take its derivative to get the critical points, which is that. And then I will divide by negative 32. And we'll do 72 by 32. And let's see here, that will give us as a decimal 2 1/4. So we'll do a number line starting at 0 here, 2 1/4. This is S prime. If I pick, say, 2 as a test point, 72 class minus 64 is a positive. If I pick, say, 3, I'll get negative 96. That's a negative. Since S prime only changes signs from positive to negative at t equals 2 1/4, there's an absolute max at t equals 2 1/4 because S prime only changes signs from positive to negative there. But what is the actual maximum height? You have to plug this back into S. And we're just going to use a calculator for that. So 80 plus 72 times 2.25 minus 16 times 2.25 squared, and I get 161 as a maximum there. And then just some of the others while I have the video here live, and some of the other ones. Here in this problem, because the derivative of f only changes signs from a positive to a negative at x equals 1, f has an absolute maximum at x equals 1 because the derivative being graphed only changes signs from a positive to negative there. Just like in this one, the derivative of f is given. So f has an absolute min at x equals 1 by the global argument because the first derivative goes from a negative to a positive. It only changes signs once at x equals 1. So it's going to be an absolute min at x equals 1. And this would be an absolute max at x equals 1. And that, oh, no. Why am I saying 1? I was right. 0. Bad. Sorry. Jeez. Can't focus here. So I'm looking here. Why do I look at 1? So at 1 up here, it's an absolute max. But down here, it's an absolute min at x equals 0. We cannot find the maximum value until we start to involve integrals. So the same thing up here. We can only argue that f has an absolute max at x equals 1 because the derivative of f, which is the graph given, only changes signs from positive to negative. And here in this one, we can only argue we have an absolute min because the derivative of f only changes from a negative to a positive. And these right here are two good problems. I guess I'll close it out with this here to have them done. Is we're to find the time when the particle is farthest to the left. So that means we're going to minimize s of t. I am on a closed interval here. So it's either the global argument or the closed candidate test. And it's going to be the closed candidate test for sure. So I'm going to take my derivative, which I know in this case is velocity, by a product rule, which is that. E to the negative t, the derivative of sine is cosine, plus the second, which is sine of t, times the derivative of the first, which is negative e to the negative t. Factoring is the name of the game to clean it up. So it's cosine of t plus sine of t equals 0. So, no, guys, I got to be careful. It's a minus there. I'm not being careful enough because a negative times a negative is a positive. Need that negative there. This is never 0. So the only way I can convert sine and cosine when they're being added to one trig function is to subtract or add cosine of t to both sides and divide by cosine of t. And tangent of t equals 1. Where is that happening at? Well, tangent's positive along a positive slope. So that reference angle is pi over 4. And the third quadrant, is 5 pi over 4. So what am I going to do? Make a table of values. The endpoints, 0 and 2 pi, and the interior critical points. E to the 0 times the sine of 0 is just 0. E to the 0 is 1, and the sine of 0 is 0. E to the negative 2 pi times the sine of 2 pi, well, sine of 2 pi again, guys, is also 0. This might be e to the negative pi over 4 times the sine of pi over 4, but the sine of pi over 4 is 1 over root 2. So I'm just going to times it by that. And this would be e to the negative 5 pi over 4 times the sine of 5 pi over 4. Now, the sine of 5 pi over 4 is negative 1 over root 2. This is a more of a, this is a positive value. So that's my maximum, where this is my minimum. So it said what time? This is my minimum value. So this would be at time equals 5 pi over 4. Man, I just might as well finish it up with this last problem, which had actually appeared on the AP exam quite a few years ago. So I am on a closed interval, and I do look that 10 minus 2 minus 1 is 7. E to the 0 is 1 times 4 is 4 plus 3 is 7. Why am I checking that? I'm checking to see if the function's continuous on a closed interval. So the closed candidate test applies. So let's go right to the derivative. It's a derivative and a table of values. So this would be minus 2 minus 2x. And this derivative would be 4e to the x minus 1, because the derivative of e is the function itself times the derivative of the exponent times 4. All right. What do I got here? I'm going to set this equal to 0. And this equals 0 when x equals minus 1. So that's a critical point there because that's within that interval. And at 1, let's see here, at 1, I'm getting -4, and at 1, I'm getting +4. So the derivative to the left of 1 is -4, and to the right of 1 is +4. These are not the same value. So therefore, x equals 1 is a critical point because the derivative at 1 is a DNE, and 1 is within that interval. So it's pretty easy because I don't have to do any number line test. I'm just going to go right to the endpoints here, -2 and 2. And again, my interior critical points are 1 and -1. So I ask you a question. Which x value do you think students mostly miss? And they always miss that critical point where the derivative does not exist. Remember, critical points occur where the derivative is 0 or the derivative does not exist. Because at those corner points where the slopes don't come together to become one value, there can be an extreme value there. There can be a max or a min. All right, how do we get the y values? Sub them back in. So it's going to be 10 plus 4 minus 4, which is 10. Put in the 1, that goes down to the bottom piece. And that's going to be 4 plus 3, which is 7. And then minus 1 is also going to go to the top. So that's 11. And then down here, the 2 is going to go to the bottom piece. Why can't I write this correctly? Now, what is this value? E is 2.718. So it's just over that, it's 2.718. So this rate here would be your maximum, and your minimum would be 7. Okay, so I did that kind of quick over here. I just want to double check my work. That's putting a -1 in for x, because x is less than 1 for the top piece. So that's 10 plus 2 minus 1, so 12 minus 1 is 11. And then e to the 0 is 1 times 4 is 4 plus 3 is 7. I have to go down to the bottom piece for when x is 1. And then when x is 2, I go to the bottom piece. And 2 minus 1 is 1, so that's going to be 3 plus 4e. And then minus 2, that's going to be 10 plus 4 minus 4, and that's 10. So I think I got it. This is the minimum is 7, and the max is 3 plus 4e. So I think I basically did all of them here, except for those 2 easier ones. This one here, you'd have to do the global argument. The derivative is 2/3 x to the minus 1/3, which would be 2 over 3x to the 1/3. And the only critical point there, guys, is 0. So when my denominator equals 0, 0 is within the domain of that function. So if I pick like a -1, take its cube root, it's going to produce a negative. If I pick 1, it's going to produce a positive. Since my derivative, k prime, only changes signs from negative to positive at x equals 0, that's where my minimum value is going to be. And if I put 0 in, I will get 0 for a y value. And this one here, too, is going to have to be a global argument. Take the derivative, so it'd be 3/2 times 1/2 x to the -1/2 minus 3/4 x to the -3/2. And then that's going to give me here 3/4 x to the 1/2 in the bottom minus 3/4 x to the 3/2 in the bottom. And what you'd have to do here is get a common denominator by multiplying by x over x. So then now this will give me 3x minus 3 over 4x to the 3 halves. Set the bottom equal to 0. X equals 0. Is that a critical point? Is it in the domain? If I put 0 back here for x, I can take the square root of 0. But here I can't throw this in the denominator. So 0 is not in the domain of that function. It's out. When does this equal 0 and x equals 1? So then if I pick here, say, 1/4, I'm going to get a negative. If I pick, say, 2, I'm going to get a positive. So this is on h prime. Since h prime only changes signs from negative to positive at x equals 1, h will have an absolute min at x equals 1. And what's the minimum value? Just substitute it back in, substitute it back in, and I'll get 3 halves plus 3 halves, which is 6 halves, which is 3. Man, that was a lot there. So hopefully I did a good job there in keeping track of all those solutions, and I hope that helps you. Again, the bottom line, the takeaway is in order to find an absolute max or an absolute min, we either do the global argument, and that's where you have to do a number line test on your first derivative and hope that it changes signs exactly once. Or we do the closed candidate test, where we build a table of values, having the endpoints we call A and B in the interior critical points. We sub all of these values back into the original function. The biggest is the max, the smallest is the min. All right.